So we've seen the change in variables from rectangular to polar, rectangular to cylindrical, and rectangular to spherical. And when we've done that, what we've seen is that when the differential has to change over, the dA or the dV, we end up getting an extra factor in there. So like in polar, we have an extra r as our factor. So, you know, we say that the dA is r dr d theta. So we've seen that the dx dy doesn't just automatically transfer over to the new variables dr and d theta. There's that extra r in there. And we've seen where that extra r comes from geometrically. And so we saw that it basically comes from the area of one of those polar sectors or the volume for one of those new polar cubes, cylindrical cubes or spherical cubes. But what if you just have a random change in variables? Because really what this is just a new type of substitution, essentially. You know, we've had U substitution previously back all the way in Calc 1 and 2. And all this is a new substitution. So, you know, we're just swapping out, you know, X for R cosine theta and Y for R sine theta, right? I mean, it's just a new substitution where one variable is getting replaced with another variable. And in this case, now we have two variables getting replaced with two other variables in a very unique type of substitution. But what if we want to do some other, you know, random logical substitution here, okay? By changing our variables that maybe doesn't have as much of a geometric tie to it. How are we going to figure out what that new differential is going to look like and what the extra factors we might possibly have in there are? Well, the way we do it is through this thing called the Jacobian, okay? And there's a formula for generating what the differential and the extra factor in the differential should look like. And so let's say we have some sort of substitution where X is going to be subbed out, let's not do that, where X is going to be subbed out for some function that has two variables in them, let's call them U and V, and Y is going to be subbed out for another function that has those same two variables in it, U and V. So X and Y are coming out, U and V are going in its place. So it's really not just like a U substitution, but a U and V substitution. And in the case of polar, it was an R and theta substitution. Then we can calculate the Jacobian of X and Y with respect to U and V, and we'll denote it like this, okay? The Jacobian of X and Y with respect to U and V, and we're using this partial derivative notation here, because partial derivative is going to be a part of it, simply by the determinant of this matrix. So if you notice what happens here, we have a couple of pieces. One, you have the first row of this matrix here. And we work with X, the X equation. We're going to take the derivative with respect to U, and we're going to take the derivative with respect to V. And then the next one, we're going to work with the Y equation. And we're going to take the derivative with respect to U and the derivative with respect to V, and that's going to be the second row. And it actually doesn't really matter which one you start with. You could start with Y as the first row or X as the second row. You could take the derivative with respect to U, V first and then U second. But whatever you do, make it consistent. So here, this whole column's with respect to U. This whole column's with respect to V. All right. Once you have that matrix set up, you just do the determinant matrix. So this times this minus this times this. And there is your Jacobian. Whatever that turns out to be, that would be the extra factor that you turn into. If we were to do this with more variables, so let's say we have three variables, X, Y, and Z. So X is this function of U, V, and let's say W. And Y is this other function of U, V, and W. And Z is this third function of U, V, and W. Well, then what you're going to get is a 3 by 3 matrix that you need to find the determinant of. So you do X with respect to U, X with respect to V, X with respect to W. And then next you do Y with respect to U, Y with respect to U, Y with respect to V, etc. And then the last one would be z with respect to u. And again, order is not so much important as long as this whole column is with respect to the same variable, this whole column is with respect to the same variable, this one, and this one's the same starting variable. So x equation, y equation, z equation. And you would find the determinant of that matrix, and that would give you the Jacobian for maybe a larger substitution. Okay? So it's a very systematic way of coming up with that extra variable there. Okay? And we could see how it worked for polar or some, again, random substitution. So here's a particular UV substitution for a set of x and for variables x and y. And why would you pick this particular substitution? Well, it depends. I mean, if you're doing an integral and pulling out x and y and replacing it with these two equations that have u and v in them makes the integration easier to do, that's why you would do it. But let's just find what the Jacobian would be. And so if we look at this, we want to find the derivative of x with respect to u, the derivative of x with respect to v, the derivative of y with respect to u, and the derivative of y with respect to v. And so what happens here is we're going to get x with respect to u is going to end up being a minus 1/2. Remember, v is a constant, so this would be minus 1/2 is a constant multiple. This would be 1. This would be 0. X with respect to v is going to be positive 1/2. Y with respect to u, I said y with respect to y there, but y with respect to u would be 1/2, and y with respect to v would be 1/2. And so if we do this determinant, minus 1/2 times a positive 1/2 is minus 1/4, minus this times this would be a 1/4, so you get minus 1/2. So that's your Jacobian. So the idea here is if you had some double integral that had a function of x and y in it, dA, okay, and you were to turn this over to a new integral here, well, you would switch out the x for a minus 1/2 u minus v. You would switch out the y for a positive 1/2 u plus v. So every time you see an x, you plug this. Every time you see a y, you plug this. And then the dA would turn into an extra minus 1/2 du dv. Okay? And so that is how we would calculate the Jacobian. Now, there's a little bit more to that. It has to do with this piece right here. What we actually end up doing is we actually do the absolute value of this. And that has a little bit to do with switching up the order into the determinant and kind of how that affects the integral. More linear algebra than maybe we need to get into right now. But for right now, that actually would have an absolute value on it. So you would actually have an extra positive 1/2 in the integral. The Jacobian is negative 1/2. But as far as how your integral would go, you would have an extra positive 1/2. So let's calculate the Jacobian for polar. We know the answer is going to be r, but let's see it in action. So we have the partial derivative of x with respect to r, the partial derivative of x with respect to theta, the partial derivative of y with respect to r, and the partial derivative of y with respect to theta. And so what you end up with here is x with respect to r would be cosine theta. X with respect to theta would be r or minus r sine theta. Y with respect to r would be sine theta. And y with respect to theta would be r cosine theta. So this times this minus this times this, we would end up with r cosine squared theta. This times this, but subtract it, we would have actually a plus r sine squared theta. If you factor out the r, you have cosine squared theta plus sine squared theta, which we all know equals 1. So what do you get? R. Okay? So you can see that's another way to find out why we need an extra r in our dA. So our dA for this polar conversion would be r dr d theta. Okay. So now we see how this is going to affect our integration. I alluded to it just a few seconds ago, but here's now the official way of seeing how it affects our integrals. So let's look at a change of variables for these double integrals. So let's let R be a vertically or horizontally simple region in the xy plane, and let S be a vertically or horizontally simple in the uv plane. So the idea is we're switching from x and y to u and v, so we want to be able to define our region in terms of x and y, but also define it in terms of u and v for our limits of integration. This also says let t from s to r be given as tu equals xy, where x is a function of u and v, and h is a function, or y is a function of u and v. This is basically just saying that there is some substitution we can make where x becomes a function of u and v, and y becomes a function of u and v. Okay, so there's just this translation that we can make, this transformation we can make from x and y to u and v. And g and h have continuous first partial derivatives. We need that because we need that for the Jacobian. So assume that t is 1-to-1 except possibly on the boundary of s. So that means we can go from, so t is this function that's taking us from x and y to u and v. It's 1-to-1 in that you can go back and forth. You can go from x to u and v, but you can also go from u and v back to x. Okay, so the 1-to-1 means you can go back and forth. If f is continuous on R and this Jacobian is non-zero, then we should be able to take this integral here that has x's and y's in it, and it's over this region R, which is in terms of x and y, and switch it over to this integral, which is now u's and v's, and the region in terms of u and v is now s. So we're integrating over this region s instead of this region R. But look at the pieces here, okay? X turns into this function of u and v, y turns into this function of u and v. The dx dy ports over to this new differential that has u and v in it, but it has the Jacobian, and not only that, it has the absolute value of the Jacobian. And again, that's really because when you find the determinant of the matrix, how you order it makes a difference. When I do this order for partial x with respect to u, partial x with respect to v, etc., and I switch around this order a little bit, and I said, remember, the order doesn't really matter. Well, when you do switch the order in the determinant, it'll change the sign of your answer. So to avoid that happening and having that affect this, because we're just picking a random order here for the Jacobian, if we take the absolute value of it, now we know that no matter which way we do it, the sign will always remain the same. So now we need to look at this particular example. Now, I'll warn you, these are not easy, and the hardest part is the limits of integration. So let's set up a couple of things we need. First off, there's a particular substitution we're going to use here, that x equals u over v plus 1 and y equals u times v over v plus 1. That would probably be one of the hardest things to do, is to come up with what substitution would work best for the given scenario. And there is no good way of doing it. It's really a matter of trial and error for how that substitution would come about. So what we're going to do is let's say we have the substitution already, okay? Because that's a pretty advanced idea of coming up with this particular substitution for this problem. It's well above where we are right now. So let's assume that we have the substitution. Here's the integral we want to do. Looks like a fairly harmless integral in terms of x and y. The problem is the region that we're integrating over. So if we look at this region and we were to sketch it out real quick in terms of x and y, this is where the problem lies. So if y equals 2x, which would be, say, this line right here that has a slope of 2, okay, that's y equals 2x. Then y equals x would be this line here, this is your 45-degree line. That's the line that has a slope of 1, okay, so it's not as steep. Then we have y equals 3 minus x, so it has a y-intercept of, say, 3, and has a negative slope, so let's go down this way. And then the other one is 6 minus x, so it has a y-intercept of 6, and it also has a slope of negative 1, so it's parallel to the previous one, and we get this. And so this is the region D that we're talking about here. Now, what's the problem with this? Well, if we tried to set this up vertically, we have a couple of issues here. There is no one function on top and one function on bottom. Right? If you look, here we have the 2x on top and the 3 minus x on the bottom. But once we get past this point here, the bottom function turns into this line. So we could cut this up into a bunch of separate pieces. So if we cut it there, maybe we cut it there, and we cut it into 3 separate groups. Here's one piece, here's another piece over here, and here's the third piece in the middle. Okay. So we could cut it up into those pieces and do 3 separate double integrals. But this is the problem with this example. So what we want to do is we want to make a substitution that makes this region a little bit easier to work with, and so this is the substitution that will do it. So what do we need? We need a couple of things. We need to convert this function over to u's and v's. We need to convert the differential over to u's and v's, and we got to look at the region in terms of u of v. And that is the hardest part. And so the function x plus y being converted into u's and v's is easy. We know x equals u over v plus 1 plus y equals uv over v plus 1. So if we put this together, we get u plus uv over v plus 1. If you factor out a u, you have 1 plus v over v plus 1. They cancel, so ultimately you just get u. So the function converts to just u. Now the differential we know is going to turn into du dv, but there also might be an extra piece on that. This Jacobian is that extra component. So what we're going to need is to do the Jacobian determinant matrix. And so we take the derivative of x with respect to u, and that'll be 1 over v plus 1. We're going to take the derivative of x with respect to v, in which case we're going to need quotient rule. So the derivative of the numerator with respect to v is going to be 0 times v plus 1 minus the derivative of the denominator, which is 1 times u all over the denominator squared. Okay? And then do the same thing with y. Y with respect to u is going to be v over v plus 1. Y with respect to v, again, we're going to need quotient rule, so it's going to be u times v plus 1 minus u times v over v plus 1 squared. So what you see here is that this is going to have to distribute in here, but this uv and this uv will cancel because they're positive and negative, so we'll just get a u. Here this is 0, so this is gone, so we just get a u in the top. So then if we do the Jacobian determinant, first one would give us, let's change color here. First one would change us to, we have a minus u over v plus 1 cubed. The next one, here times here, would give us a minus uv over v, where are we at here, v plus 1 cubed. But that's being subtracted, so actually it's going to end up being a plus. Okay. Actually, no, there's a mistake here. This would be u here, so this is actually a positive u. This u and this v here would already have been canceled. So this times this would have given me positive u over v plus 1 cubed. And then this would be positive because this would be negative, but then you're subtracting it, so positive. All right, so we could simplify this, though, because when you add the top, you could pull out a u. We get a v plus 1 over v plus 1 cubed, so they'll cancel, and I'll have a v plus 1 squared. So my Jacobian is u over v plus 1 squared. So there's my Jacobian. So there's the Jacobian. That's the function that's going to switch over. So really the big problem is this right here. Here's where we're at. We have this double integral where the function is now u. The Jacobian was u over v plus 1 squared, and the new variable is du and dv for our differential. So this is the integral we need to work with. Okay. Now, what we need to do is figure out what our limits of integration are going to be for this new region. And so we have the equations, if you remember. The equations we started off with were y equals 2x, y equals x, y equals 3 minus x, and y equals 6 minus x. And we need to convert those over to u and v equations so we can sketch it out in the uv axis. Okay? And so, remember our substitution was x equals u over v plus 1 and y equals uv over v plus 1. All right, so let's start working with this and try and convert this over. Remember, our new system is going to be a uv axis system that we're going to try and draw on. So let's start with, let's start with these two down here. I think these are going to end up being easier. So let's work with that. It doesn't really actually matter where we start. But what we're going to do is you're just going to plug what x equals and what y equals into the equation and see what happens. So let's start with the y equals 3 minus x. So y is vu over v plus 1. And we have 3 minus x, which is u over v plus 1. So then if I add this over to the other side of the equation, I'm going to get vu plus u all over v plus 1 equals 3. But if I factor out a u, I get u times v plus 1 over v plus 1 equals 3. Well, the v plus 1's cancel, so u equals 3. So there's one equation. U equals 3 would be here. It would be this vertical line there. Okay? All right, let's keep moving. Let's try the other one. So y equals 6 minus x. Well, you probably assume that the same thing is going to happen. So y is u times v over v plus 1. Let's put a line here. You have 6 minus u over v plus 1. In which case this is going to add over, all the same stuff's going to happen. I'm going to get u equals 6. So if u equals 6, here is that vertical line, u equals 6. Okay. Now let's work with some of these other ones. Let's look at this one, y equals x. So what do we have? We have u times v over v plus 1. Equals u over v plus 1. I'll do a lot of the same stuff, move this over to the other side, in which case I'm going to have u v minus u all over v plus 1 equals 0. Now, if this is a fraction equals 0, the only way this fraction equals 0 is the numerator equals 0, so we can basically get rid of this. And so what we have is factor out a u, we have u times v minus 1 equals 0. And now we have a zero product property, so u equals 0 or v equals 1. So we got two things out of this one. U equals 0, which now we're here. We have this equation, u equals 0. And we have v equals 1. Well, here's the v-axis, so v equals 1 would be this line right here. Okay. And then finally, what do we have? The last one, the y equals 2x. So we are saying that y is u over v, u times v over v plus 1. We have 2 times u over v plus 1. Do the same thing, move it over, uv minus 2u over v plus 1 equals 0. Again, being that the fraction equal to 0, we can ignore the denominator, such as this equals 0. Pull out the u, we have v minus 2 equals 0. So you have u equals 0 and v equals 2. So the only thing new here is the v equals 2. So there's v equals 2 there. So then what is basically bounded by all this? Well, we have three u's here. We have this u, we have this u, and we have this u. So as far as the total width for U, we go from here to here. And the V's are going between here and here. So this is essentially our new box, right? This is our new domain. Let's call this S. So it's pretty easy to say, well, what's U between? U is between 0 and 6, and V is between 1 and 2. So as far as our limits of integration goes, that's it. And the nice thing is they're constants, right? Constants for U, constants for V. So now that we have our limits of integration, we have our integral, we got everything we need to finish this thing off. So let's finish this off now. I told you this was not going to be easy. So we have a double integral. The function U is what we're integrating. We have this new piece of the differential, which is U over V plus 1 squared. And we have du and dv. Now the order, we can mess around with that order. Since everything's a constant, we really can easily mix around the order, but U was between 0 and 6, and V was between 1 and 2. If you notice in this case, we could do U first, but we also have a product of two single variable functions in here, so we could pull this apart completely. And I could do the integral from 1 to 2 of 1 over V plus 1 squared dv times the integral from 0 to 6 of U squared du. I could pull it apart like this, and it's even easier for me. And I can only do that, one, because the limits of integration are constant all the way across the board. And this is a function of two single variable functions multiplied together, right? It's essentially a function of U times a function of V, where the function of V is here and the function of U is here. All right, so let's do this. This 1 over V plus 1 squared, in order to integrate that, we're going to need to do a substitution. It seems a little silly, but we're going to need to do that. Let's say T equals V plus 1, dt equals dv. So we end up with just the integral of dt over t squared, which would be the integral of t to the negative 2 dt. So we're going to use our simple power rule here. And what do we end up with? Well, we're going to add 1, divide by, so we negative 1 over t, essentially t being v plus 1, and that's going to be between 1 and 2. That's multiplied by this one, which is even easier, so that's going to be u cubed over 3, so u cubed over 3 between 0 and 6. So then we plug in 2, we plug in 1 into this piece, we plug in 6 and 0 into this piece, multiply them together, there's our answer. So what are we going to get here? Negative 1 over 3 plus 1 over 2, and this will be 6 cubed over 3 minus 0 cubed over 3. So in the end, we end up with, so we'll get 1/6 times 6 to the third, which is 216 over 3. So 216 over 18, which is actually going to be 36 over 3. So 36 over 3 would give me 12. Okay? So there's the answer, 12. Seems like a simple answer for such a complicated problem, but that's it. That's the reason why we went through all this. Now, we could have, like I said, left it in terms of x and y, did 3 separate double integrals, and maybe you go, well, that probably would have been easier in the long run. Let's just go back and do that. You could go ahead and do that and add those 3 integrals together, 3 double integrals together. But this is just showing you how you could do a change in variables. And again, it's not easy. It's not an easy conversion, especially when it's not very geometric in terms of like polar or cylindrical, where it's just this random substitution, and you have to see what the new thing is, the new domain is. But once you look at that new domain, and we saw that really turned into a simple rectangle, this is the reason why this substitution was chosen for this problem.